Imagine you have 10 light bulbs. You can toggle each one of them on and off. Could you represent numbers with them? Perhaps you already have an idea of how you could represent natural or whole numbers. But how about fractions of whole numbers? Could you even represent irrational or complex numbers? This question may sound absurd, but one answer to it has made the digital world we live in today possible in the first place. For this purpose, an international standard was formulated in 1985, which is now implemented in almost all computer systems. In this video, we will rediscover that standard intuitively. So let's start with natural numbers. We could, for example, decide that the number simply corresponds to the number of light bulbs that are lit. If we told someone else about this rule and they saw 3 light bulbs turned on, they would know that we are representing the number 3. If all of them are on, the number 10 is meant. If none are on, the number 0 is interpreted. This allows us to represent the following 11 natural numbers. Not bad for a start, but more numbers would be welcome. In addition, the numbers from 1 to 9 don't have a unique representation. For instance, we get the number 2 when these 2 light bulbs are on, but also when these 2 are on. We will see why this is a problem in a moment. First, let's try to establish another rule. Perhaps it would make sense to number the light bulbs, starting with the first one on the right, ending with the 10th one on the left. We can now establish the rule that the number simply corresponds to the position of the light bulb that is lit. For example, if the 3rd light bulb is on, the number 3 is meant. If none are lit, the number should correspond to 0 again. With this rule, we can represent the same 11 numbers, but each number now has a unique representation. Let's try to further expand this concept. See, in its current form, only one light bulb can be lit at a time. How could we adjust the rule for multiple light bulbs to be on simultaneously? Well, one option would be to just add up the positions of lit light bulbs. So if the 4th and 8th light bulbs are on, we represent the number 8 plus 4, which is 12. If all of them are on, we get 55. With this rule, we can now represent 56 numbers, but unfortunately, we have again ended up with numbers that have multiple representations. The importance of uniqueness becomes clear when we answer the following question. How many numbers can we actually represent? Let's assume we only have 2 light bulbs. If both are off, we can assign this configuration to any number, as we just did with the 0. But there are other configurations for these light bulbs, such as right one on, left one off, left one on, right one off, and finally both on. So with 2 light bulbs, we can represent a total of 4 different numbers. And how could we have calculated that? Well, the first light bulb can be in 2 states. The same applies to the second. For both together, there are therefore 2 times 2, so 4 different configurations. If we add another light bulb with 2 states, there are a total of 8 configurations for the 3 of them. In general, we can get the number of all configurations by raising 2 to the power of the number of light bulbs we have. We can therefore represent a total of 1024 different numbers with our 10 light bulbs. However, if we have several configurations mapping to the same number, we waste some of our 1024 configurations on this exact number, and can therefore represent fewer numbers overall. So we need to improve our current concept. Our 0 is unique. We only get it when all light bulbs are off. We only get the number 1 when the first light bulb is on, and the number 2 when the second one is on. For the number 3, we find 2 configurations. Either the 3rd light bulb is on or the first 2 are on. So we don't need the number 3 up there if we can already represent it with the first 2 light bulbs. And what number should we replace it with? Well, the next number on our number line that we cannot represent with the first 2 is 4. This not only makes our 3 unique, we even win a new number. If all light bulbs are on, we get the number 56. Great, let's continue. Because we now have 4 in the 3rd position, this 4 is obsolete. So let's replace it with, well, what numbers can we represent with the first 3 ones now? After 3, we can represent 4, 5, 6, and 7. Therefore, the next number we cannot represent is 8. Perhaps we can already see a pattern. So far, each new digit is just the double of the previous one. By continuing this pattern, we find that we can also write the above values more compactly as powers of 2. As this is somewhat unfamiliar, let us display the values again. With this concept, every number is unique. For instance, if these light bulbs are lit, we get the number 64 plus 8 plus 1, which is 73. There is no other configuration for 73. And how would you represent the number 42? Feel free to pause here for a moment. Well, the largest power of 2 that fits into 42 is 32. The next one is 8, and finally 2. The largest number we can now represent is 1023. The smallest one is still 0. So with this concept, we have managed to represent 1024 different natural numbers and thus made full use of all configurations. Now, to represent negative numbers, we could, for example, add a fixed minus sign to our rules. This would work, but unfortunately, we would lose all the positive ones. We somehow need a sign that we can set to plus or minus ourselves. To do this, we can use the last light bulb as a switch. Let's say if this light bulb is off, we interpret it as a plus, and if it is on, as a minus. That way, we can represent 19 like this and minus 19 like this. With this set of rules, we can represent numbers from minus 511 to plus 511. So there are just as many negative numbers as positive ones. But out of 1024 possible numbers, we got only 1023. So somewhere there's a non-unique number. And that's 0. Of course, with this concept we get a plus 0 and a minus 0. In arithmetic, these are of course the same numbers. But we could also view them as different numbers. See, when calculating limits, the result can be different depending on whether we approach 0 from the negative or the positive side. So let's rather be happy that we can represent a plus and a minus 0. So we now know how to represent integers. The next challenge is to represent rational numbers, which are fractions of whole numbers. Let's take a closer look at such a number. In everyday life, we often see fractions in the form of decimal numbers. These consist of a sign, an integer, and a fraction after the decimal point. In this case, the integer part consists of 6 ones, 4 tenths, and 100. The fractional part consists of 7 tenths and 5 hundredths. So this number contains 6 times the number 1, 4 times the number 10, and so on. These place values are all powers of 10, with positive exponents in the integer part and negative exponents in the fractional part. This concept is very similar to that of our light bulbs, with the difference that we use the base 2 instead of base 10 and do not have any fractions. But we can try to copy the idea. Let's also take a point and place it, for example, in the middle. For the whole number, we use the same concept as before, and for the fractional part, we expand with negative exponents. Let's show the decimal values again for convenience. And indeed, we can use this to represent numbers such as 4.125 or minus 4.625, all of which are unique because we cannot represent a specific value in the fractional part by using other configurations. So, the largest number we can represent is this one, and the smallest is the negative of that. That's not a large range, but inside there are a total of 1024 numbers we can represent. This means that there are 31 rational numbers between two whole numbers. Looking at the red dot, I remind you again of the difference between plus and minus 0. Alright, we completed the challenge and could now move on to the next one, but this representation is not yet entirely satisfactory. See, we arbitrarily placed the point in the middle. If we had placed it one place further to the right instead, we could represent numbers in a much larger range. But at the expense of accuracy between whole numbers, because we can now only represent 15 of them. So where should we ideally place the point? Well, that depends on what numbers we want, either small or large ones in terms of magnitude. A more elegant solution would be if we could always place the point where we need it. However, to do this, we would have to integrate a set of rules that moves the point to the desired position. Perhaps we can copy an idea from the decimal system again. For example, if we want to move the decimal point of a decimal number one place to the right, we simply multiply the number by 10. If we multiply by 10 again, we have effectively moved the decimal point 2 places to the right. If we want to move the decimal point to the left, we simply divide by 10 or multiply by 10 to the power of -1 or to the power of -2 and so on. A decimal number can therefore also be constructed as follows. We represent any decimal number and move the decimal point to the desired position by multiplying by a power of 10. Let's again replace the base 10 with 2 for our light bulbs and implement this idea. The only elements we need to represent by switching the light bulbs on and off are the sign, a number with a point, and an exponent. We can simply add the base 2 and the multiplication point in our minds, as these do not change. Okay, we already have the sign. For the point number, we'll just reserve a few light bulbs with our current concept and use the rest for the exponent. For this, we need positive integers for our shift to the right, negative integers for our shift to the left, and a 0 so that the point stays in its current position. So we could use our concept for whole numbers, right? Well, yes, but having a plus and -0 doesn't make sense in this case. But we can fix this. What if we instead represent only positive numbers, but we always subtract a fixed value which we call bias? See, with no bias, we can represent the numbers 0 to 15 with those 4 light bulbs, all of which are unique. If we subtract a fixed value like 3 from each number, we can represent numbers from -3 to 12 without having a double 0. Ideally, we should choose a bias that lets us represent just as many negative numbers as positive ones. Without the number 0, we could represent a total of 15 positive and negative numbers, which cannot be divided evenly in half. So let's choose a bias of 7, which allows us to represent 8 positive and 7 negative numbers. Okay, let's test it. If these light bulbs are on, we get the number -1.25, because the sign is negative and the exponent corresponds to the number 7 minus the bias 7, which is 0. This means we simply multiply our part with the point, which corresponds to the value 1.25, by 1. We would have gotten the same result if we didn't have the part with the exponent at all. But let's now take a look at what happens when we increase the exponent by 1, so that our point part is multiplied by 2 to the power of 1, which is 2. We get the number -2.5. How could we have represented this number without the exponent? Well, we would have had to move the fixed point one place to the right. So, it's working. We don't have to decide where to put a fixed point, our exponent takes care of it. In contrast to the base 10 system, where moving the point to the right corresponds to multiplying the number by 10, in our base 2 system, we have to double the number. To move the point to the left, we have to halve the number. However, we can also double or halve certain numbers without changing the exponent. For instance, this configuration corresponds to the number 0.125. Here, the exponent is 0 overall, so we don't move the point. If we instead turn on this light bulb, we get the number 0.25. So we have doubled our number. We could halve this number again by reducing the exponent by 1. And this is where the problem becomes apparent. We get the number 0.125 again, but the configuration of the light bulbs is different this time. So this number does not have a unique representation. Even worse, we can double this number in the point part again and get the number 0.25 again, which means it is also not unique. We can even continue this little game. Half again with the exponent, double with the point part, and half again with the exponent. The game of cat and mouse only ends when the last light bulb in the point part, that is, our only integer digit, lights up and we can no longer double here, no matter which light bulbs we additionally switch on in this part. In other words, as long as the integer light bulb with the value 1 is lit, all numbers are unique. So let's just leave this light bulb on all the time? Well, if it's always going to be on anyway, we could integrate that as a fixed rule and use the fifth light bulb for an additional fractional place. As a result, the light bulbs in this part now only consist of fractional values, for which there is a specific term, the mantissa. With this set of rules, all 1024 configurations are uniquely assigned. For example, the number 0.125 can only be represented in this way. And we can also represent small and large numbers in terms of magnitude. The only problem we now have to solve is that we have lost our plus and minus 0. If all the light bulbs are off, we get a number close to 0, but not exactly 0, because we always have a little bit of value due to the fixed 1. However, our current concept is pretty good, so we should not make any major changes now. Let's just integrate a special case. Let's say that when all the light bulbs in the exponent are off, and it is therefore as small as possible, we no longer use this configuration for this small number, but we use it for a rule change. Only in this case, we no longer imagine the 1 before the point, but a 0. This not only brings us back our plus and minus 0, we now can represent numbers that are even closer to 0, all of which have unique representations, because for every other exponent, the 1 before the point is active again. Speaking of special cases, are there any other useful ones we could formulate? For example, what could we represent when the exponent is largest? That is, when we are representing a very large or very small number in terms of magnitude. How about sacrificing these numbers for the expressions plus and minus infinity? Okay, but having several configurations for plus and minus infinity isn't useful. Let's say we only represent plus and minus infinity when the mantissa is 0. And when it's not 0, we use this configuration for something else. How about nan, which stands for not a number? We could use this if someone asks us to represent a fraction like 1 divided by 0, which, as we know, cannot correspond to any number. Now, there are several configurations for a mantissa not being 0, and we can also change the sign. Does this mean that the expression not a number is not unique? Well, yes, but only if we always made the same nan. We could also represent different nans. For instance, one for the case of dividing by 0, or one for the case of taking the logarithm of a negative number, and so on. And with that, we are done. Our rules seem to be perfect. The only thing left to think about is how many light bulbs we should use for the exponent and the mantissa respectively. The more we give to the exponent, the larger the range in which we can represent numbers. However, these will be further apart, so we lose accuracy. On the other hand, the more light bulbs we give to the mantissa, the greater the accuracy, but in a narrower range. So we have to accept a trade-off. With our current concept for rational numbers, we cannot represent irrational ones. So should we look for a new concept? Well, an irrational number such as pi not only has an infinite number of decimal places, but these places also do not form a repeating pattern. In a sense, such a number contains an infinite amount of information. To represent this, we would need an infinite number of light bulbs, which is slightly more than we have at our disposal. So the best we can do is to approximate irrational numbers using our current set of rules. With complex numbers, it's different. A complex number is a two-dimensional number consisting of a real part A and an imaginary part B, which are real numbers. Although we cannot represent irrational numbers, we can represent rational ones. So we can represent complex numbers with rational real and imaginary parts by using our current concept. Instead of using 10 light bulbs for one rational number, we can represent two rational numbers with 5 light bulbs each. Since the imaginary unit I is part of every complex number, we can integrate it as a fixed rule. Okay, what does all of this have to do with the digital world? Well, the person we taught these rules is actually a computer, where numbers are represented in exactly this way. To do this, a modern computer such as your smartphone contains billions of light bulbs, although these are not conventional light bulbs but so-called transistors. However, these work in a similar way to a light bulb. They can also be toggled on and off depending on the voltage applied. But compared to a conventional light bulb, a transistor is about this big. And when we humans want to write down a number that the computer can understand, we don't draw on and off light bulbs or transistors every time, but instead use the symbols 1 and 0 and call them bits. If a computer can work with numbers, then it can also work with anything that we can represent in the form of numbers. Every text, every sound, every image, and every video is just a collection of numbers for the computer. For instance, a text consists of letters and special characters, which we can number one after the other. A sound is nothing more than sound waves, in other words, changes in air pressure. To represent this, we can tell the computer how much the speaker needs to oscillate each time. An image consists of a series of small colored squares known as pixels. Now, the human eye only has receptors for the primary colors red, green, and blue. Depending on how strongly the individual receptors are stimulated, our brain mixes these components together and we see other colors such as purple or brown. We can therefore equip a pixel with 3 LEDs in the colors red, green, and blue and tell the computer how intensive each LED should shine. Our brain then mixes the desired color for us. And a video is just a sequence of images and sounds. In addition to this data, there's a lot more, but for the computer it's all just zeros and ones. And in order for a computer to know that a certain sequence of numbers corresponds to a text and not an image or something else, file formats were developed. So all bits in a text file are interpreted as letters or special characters, and so on. Can you think of an even better way to represent numbers on a computer? You could be the one to open up a whole new digital world.